Units. So back in 1999, NASA lost the $125 million Mars Climate Orbiter. They sent it up there, it began to orbit Mars, and it descended too far, got trapped in the gravitational pull and burned up. Oops, $125 million. So of course there's an investigation, right? The chairman of the committee investigating this disaster concluded the root cause of the loss of the spacecraft was a failed translation of English units into metric units. What? Somebody was using inches, somebody else was using centimeters, and they didn't convert correctly or didn't communicate the units correctly. Sometimes I think this happened just as an awesome illustration for intro chemistry classes, right? No, it was just really a disaster. Units are really important.
I have no idea why we don't use a metric system.
I don't either. Metric system rules. Ooh, that was a pun. Sorry. So, units are really important. They quantify. They're standards that we use to quantify length and mass and all these different properties. I'm just going to stop now. I don't know where that sentence is going. Two common unit systems, the metric system and the English system. Americans, sometimes I think we just want to be different and ornery. I think really we're just stubborn and we don't want to change. We're afraid of the metric system, and so everybody's clinging onto it. You could probably, write a master's thesis studying that, but it is what it is. So scientists use the International System of Units, or the SI system. And the abbreviation comes from the French phrase, which I'm not even going to try to pronounce. But they, like many other languages, the system comes first and then international. That's why it's SI. The SI system is based on the metric system, and as far as I'm concerned, the differences between the two are completely insignificant. They matter not at all. So I will refer to the metric system and the SI system pretty much interchangeably, but right now I am acknowledging there are subtle differences, but I'm ignoring them because I can. These are the base units in the SI system. Quantities are length, mass, time, temperature, amount of substance, electric current, and luminous intensity. These last two are not going to come up in this class at all. Length is meter, mass kilogram, time is a second, and that's the same second that we're familiar with. Temperature is the Kelvin, and the amount of substance is a mole. And we are going to learn about all of these. Their symbols are over here, and there are some places where details are really, really important. The abbreviation for a meter is a lowercase m. It's not ME period. It's not MTR, it's not a capital M, it's just a lowercase m. And we have come up with these symbols as a shorthand to make all of the stuff a lot more concise so we don't have to write out all these long words. But then we have all agreed to use the same symbols so that we don't misunderstand each other. Because you know what happens when you send off an important email and you've got one letter wrong in the address? It doesn't get there. And you lose out on something or you get in trouble, right? Well, that L, that lowercase l, looks like a 1. Why didn't the computer understand it? Because it's different. There are times when details matter. So we need to have a rough idea of how big these quantities are. That can make us immune to some silly mistakes. Like if you do a calculation and you find out that this person is 7 meters tall. Well, if you know how big a meter is, you could recognize that that's ridiculous, right? Where'd it go? Here it is. This is a meter. 7 meters? Maybe 2. Even a really tall basketball player wouldn't even be 3 meters tall. A meter is roughly the same size as a yard. It's actually 39.37 inches. You don't need to memorize that. But I want you to know that a meter is about the same size as a yard. We have very precise definitions for the meter. It's there for your amusement or edification or something, but I'm not going to test you on that. Mass is measured with kilograms or grams. So a kilogram is about 2 pounds. 2 pounds, 3 ounces, or 2.2 pounds. So someone who weighs 50 kilograms, well, that's about 100 pounds. Okay? Just have a rough idea of what a kilogram is, right? Could you carry 20 kilograms on your back? Yeah, it'd be heavy, but you could. 40 kilograms, it's like a 6-year-old kid riding on your back, right? You could do that. Another common unit of mass, and the most common one we use in chemistry, is a gram. So a gram is 1/1000th of a kilogram. And a gram is a much smaller quantity, so how do we reference that? Well, a nickel, a 5-cent piece, weighs about 5 grams. So that can give you a grasp on how much a gram is. A nickel is 5 grams. Mass and weight are not the same thing. Weight is actually a force. It's a gravitational pull on matter, and mass measures quantity of matter. So if you step on the bathroom scale and you weigh 180 pounds, and then you take your scale and you get in a spaceship and you go to the moon, you're going to weigh 3 pounds on the moon. No, 30 pounds, sorry. This is what happens when I do math in my head. 30 pounds, 1/6. I'm making this up as I go along. I was trying to make up an example that I could do. So if you weigh 180 pounds on the Earth, you'll weigh 30 pounds, 1/6 of that on the moon, because the gravitational pull is 1/6 as strong. Does that mean you're super, super skinny? Nope. You are the exact same shape that you were. You didn't lose any matter, right? You didn't lose any mass. Your mass is the same regardless of where in the universe you are. Now, on the Earth, the gravitational pull does vary a little bit, but not enough that we need to worry about it. So pretty much if you stay on Earth, we can use the terms mass and weight interchangeably, but just I have informed you that they are different things. Time is measured in seconds. That's not a big deal. We have a very specific definition of what the second is. Kelvin is a measure of temperature. So temperature is the average amount of kinetic energy of the particles in a piece of matter. So right now, in my solid state of students here, the temperature is pretty low. If we all started chair dancing, that would be a warmer solid. As things warm up, they will eventually, change state. So temperature is average kinetic energy. It tells us how thermal energy is going to transfer. When thermal energy moves from one substance to another, we call that heat. Heat is the transfer of thermal energy. It always goes from the hot object to the cold object. So temperature helps us to know what direction that transfer is happening in. So Kelvin scale is based on the concept of absolute zero. So if temperature is average kinetic energy, on the Kelvin scale, a temperature of 0 means that the average kinetic energy is 0. That means that all motion of atoms and molecules has stopped. That would mean all of you were literally petrified, right? Nothing in you was moving. Your blood wasn't flowing, you weren't breathing or blinking or anything, you'd all be dead. Yes?
Temperature in space?
I don't know what the temperature in space is. It's pretty cold, but it's not absolute zero. I don't know. That's a good question. I wonder if Siri knows. Hey Siri, what is the temperature in outer space?
I didn't find anything for what is the temperature in outer space.
Awesome. She doesn't know either. We could Google that later. So the Kelvin temperature scale is based on 0 being the lowest possible temperature. You couldn't go any lower than that because how could you have less than no kinetic energy? It's not possible, right? So here's our familiar Fahrenheit scale. You know, they say, oh, the temperature is going to be 97 degrees. 97 degrees Fahrenheit. On the Fahrenheit scale, water freezes at 32 degrees and boils at 212 degrees. Seems kind of random. There's some history behind that, but we won't go into it. On the Celsius scale, they decided, well, you know, let's make something that's a little more based on factors of 10 and a little more, I don't know, maybe easier to remember. So on the Celsius scale, water freezes at 0 and boils at 100. And you think about it, you know, how do you set a temperature, right? You say, oh, well, this temperature is some number. You need some reference point, right? So water always boils at the same temperature, always freezes at the same temperature. And so we can use those as reference points for a temperature scale. So the difference between Fahrenheit and Celsius is 0 is not in the same place, and the size of the degree is different. So that makes the conversion between the two a bit complicated. Between Celsius and Fahrenheit and Kelvin, it's the same size of unit. A Kelvin, not a degree Kelvin, and a Celsius degree are the same size. All that's different is they're offset from 0. The 0 is different. So the Celsius scale and the Fahrenheit scale, the conversion is this equation right here. The temperature in Fahrenheit minus 32 divided by 1.8 will give you the Celsius temperature. To convert Celsius to Kelvin, we just add 273.15. You have to use formulas to convert temperatures. So let's do one, and then I think we're done. So gallium's a solid metal at room temperature, but will melt to a liquid in your hand. I wish I could have some of this and just play around with it. How cool is that? A metal, and then you just hold it and it melts. Crazy. Melting point is 85.6 degrees Fahrenheit. So what is this temperature on the Celsius scale and on the Kelvin scale? So they're asking us to convert the temperature. Well, we need the equation, and you need to memorize these equations. So the Celsius temperature will equal the Fahrenheit temperature minus 32 divided by 1.8. Having an argument with my stylus here. So we are given the Fahrenheit temperature. So we're going to stick that in, 85.6, subtract 32. Very important to finish that subtraction before you divide by 1.8. So 85.6 minus 32 equals, divided by 1.8 equals 29.8. And so the unit there would be degrees Celsius. Any questions? You should always bring your calculator to class, and when I do calculations, you should do the calculations too. One of the reasons I do them like this, where I'm writing on the screen instead of just having them flash up there, is it slows me down. I am doing it at actual speed. Yes? We haven't technically learned about sig figs yet, so I am following the rules for sig figs, but I'm not talking about it. Thursday. So there's our Celsius temperature. How do we get the Kelvin temperature? Add 273. So Kelvin equals degrees Celsius plus 273.15, 29.8 plus 273.15 equals. Yeah, so the calculator says 302.9277778. So I'm going to call that 302.9. And the unit is capital K, no degree sign. Any questions?